So good morning, everyone. This is Rudrashan, and today is the second week of TA discussion, live TA discussion of Advanced Linear Continuous Control System, which is the course which is taken by Professor Yogesh Hote. And today we will discuss about the another two type of canonical models, which is diagonal canonical form and Jordan canonical form. So in the previous week, we have discussed we have discussed the companion form of matrices of systems, which are first one is a controllable canonical form and then observable canonical form. And today we'll discuss about another two type of canonical forms, which are diagonal canonical form and Jordan canonical form. Now in the state model, basically this canonical form which I'm going to talk about in today's discussion. Here basically you can see the system matrix, that matrix have basically the minimum number of non-zero elements. So basically the we basically in diagonal canonical form, you can see that the all the non-zero terms are in the diagonal positions, and all the off diagonal elements are zeros. In the Jordan canonical form, it is also a diagonal canonical form, but it is not exact diagonal canonical form. So you can, so you will see when I will discuss about it in this discussion. So let me share my screen first. So, yeah. So I hope everyone can see my screen, see the shared screen. Okay. So now, so here in today's discussion, so first is diagonal canonical form. First, I'm going to discuss about diagonal canonical form. Then I will show I will explain it with some examples, and then we'll move to the Jordan canonical form. So my screen is visible to you, right, Puneet? Uh,
Yes, am I audible?
yeah, you're audible. Yeah. So my screen
Yes,
is visible to you, right?
yes, it is visible.
Yeah. Okay. So basically today I'm going to discuss about two other canonical forms of systems, system matrices, which are diagonal canonical form and Jordan canonical form. So basically, previous week we have discussed about the two companion form, which are controllable canonical form and the observable canonical form. And now I'm going to discuss about the diagonal and the Jordan canonical form. So in this canonical form, which I'm going to discuss about this today. So in this canonical form, basically the non-zero element, you can see that there are minimum number of non-zero elements. So basically, you can see in diagonal canonical form, all the non-zero elements are in the diagonal. And in the Jordan canonical form, here also all the non-zero elements in the diagonal, but in a different structure. You can see when I'm going to discuss it about. So first, in the diagonal canonical form, I'm going to discuss about the first case. So case one is strictly proper function. So I hope you know, because previous year class I have discussed that what is strictly proper function. It is the numerator has a less number of degree than the denominator. I mean the number of poles is greater than the number of zeros per system. So for case of strictly proper function, let's say this is my
The D is
trans.
zero. The D is
Yes.
zero. D. The D is zero, right?
The D
Y
is
equal
0.
to
Exactly. Yeah, yeah. The D will become 0 basically when we transfer this transfer functions to a state space model. So we see that we get the A matrix, B matrix, and C matrix, but the D matrix is basically 0 over here. That means we have a less number of zeros than poles. So uh, so let's say this is a transfer function, and so a2 s square plus a1 s plus a naught divided by b3 s cube plus b2 s square plus b1 s plus b0. So first of all, this diagonal canonical form, we can get this diagonal canonical form only when the numerator, sorry, the denominator have a distinct number of roots. Okay, if you have a numerator a distinct number of roots, so diagonal canonical form can be possible if denominator of transfer function has distinct number of roots. Okay, so
you mean poles. You mean poles, distinct number of poles.
a distinct number of poles or distinct number, I mean the roots, obviously, if you basically this is the cat, if you I mean we can say the poles are basically the roots of the denominator and the zeros are basically the roots of the numerator. Okay, so basically distinct number of poles, distinct number of roots, distinct number of eigenvalues, all you can say is a similar kind of thing. Okay,
But
so
this our
yeah,
that
hello.
that is canonical form, right? The other form, Jordan canonical form. It
In the
has
Jordan
multiple
canonical
rules.
form, yeah,
They
in
are
the
not
Jordan
distinct.
canonical form, in the Jordan canonical form, we have a similar. I mean, it's not possible that all the roots are distinct. It may possible that sometimes the eigenvalues are similar. The eigenvalues of a matrix are the similar, or the two eigenvalues of are similar, and other two are distinct. So in that case scenario, we get Jordan canonical form. But when we can
But
say
it will
that
not be
the
diagonal. Then it will not be diagonal canonical form.
no, then it not be diagonal canonical, exactly diagonal canonical, because we get the
Okay.
all the eigenvalues or all the poles in the diagonal of the system, but we can see that in the off diagonal there is some one,
Yes,
the
yes,
element
yes,
one is
yes,
there. So it is not
yes.
exact diagonal, but it's a kind of semi-diagonal or kind of upper triangular kind of matrix you
Okay.
will
So
get.
by definition, they are not diagonal. Means
No,
Jordan
no,
is
no.
not diagonal.
Jordan is
Okay.
not exactly diagonal form. It is not exactly diagonal form. So further
Okay.
in the in further classes, I mean further lectures, you can see that when we these basically are the transformations of matrix. So when we do some kind of similar transformation, similarity transformations, so sometimes we can say if a system matrix, if a system has a different eigenvalues, that means the matrix A, the eigenvalues of matrix A are the different, then we can say the system is diagonalizable. That means when we do the similarity transform, we can see that all the matrix, all the eigenvalues of the matrix comes into the diagonal form. But if we can say, if there is a possibility the eigenvalues are not similar, sorry, are not distinct in nature. That means so distinct eigen. So do you have in? I mean, do you know the what is eigenvalue and eigenvector, right? I suppose
Yes.
you know
Yes.
what is eigenvalue and
Yeah.
eigenvector. So so let me explain just a bit. So eigenvector is basically we know that when we multiply a vector with a matrix, okay,
Yeah.
so the direction of the vector can be changed, but eigenvector are only those vector whose direction are not changed. That is the same thing, but it can be scaled. Okay, so let me take a detour from here. So and just make a node box over here. eigenvalues and eigenvectors. So we know, so let V is a vector. Okay. Now, if we multiply this vector with a matrix, okay, so obviously that matrix has to, whatever, if we multiply this vector with a matrix, if the direction of the matrix, if the direction of the matrix, sorry, of the vector, if the direction of the vector does not change, we call those vector as eigenvector of that matrix. Sometimes this eigenvector are also called characteristic vector. So there are different type of names. So basically, because we know that AV equals to lambda V. So lambda is basically the scaling parameter. So we know that if we multiply, if let's say lambda is equals to 1, so if we multiply A into V, then we get a V. That means the direction of the vector is not changing. It's basically the same vector, or it is 2V or minus 2V, whatever it is. So the direction of the vector is not changing. It is the same vector. So this special type of vector we call eigenvector, and the scaling parameters we call the eigenvalue. So here basically when in the next classes or in the successive classes, basically when you get to know what is the similarity transformation something, so we will see that you can diagonalize the matrix if the matrix have distinct eigenvalue, because distinct eigenvalue gives a distinct eigenvector. Okay, so that's why distinct eigen, so that's why we can diagonalize those matrices. So I'm not going to detail into that, but sometimes this matrix does not have a distinct eigenvalue. In those case, is it mean that we cannot diagonalize it? No, we cannot properly diagonalize it, but we can a semi-diagonalized kind of scenarios, which is called Jordan block or Jordan form. So in Jordan form, all the eigenvalues basically in the diagonal, but there are others element one over there. So now just since you have, I'm just going to just discuss little bit how this diagonal canonical form comes for the strictly proper function. So what we are, okay, so we here basically, so this is our system ys by us. So we basically we do the partial fraction. That means let's say the, okay, so let the roots of the denominator are, since obviously this is s cube, I mean the power of s is 3, so obviously there are lambda 1, lambda 2 and lambda 3. So in that case we do the partial fraction. So let's say c1 by s plus lambda 1, c2 by s plus lambda 2 and c3 by s plus lambda 3. So as you know that the partial fraction only possible if the system have a if the system's numerator have a smaller degree than the denominator. So now we have to find out the C1, C2 and C3. So there is a various possibility. I mean, you know the how to find out the C1, C2 plus C1, C2 and C3. So you have to just compare it with like A2 square plus A1 S plus A naught is equals to C1 into S plus lambda 2 S plus lambda 3 plus C2 S plus lambda 1 S plus lambda 3 plus C3 S plus lambda 1 and S plus lambda 2. Okay. So either you compare, you just multiply this portion and then compare with A2 with the constant term, sorry, the coefficient of S square with the coefficient of here S square, then you can find out. And the another thing you can do that first, replace s with a minus lambda 1. If you replace this s with minus lambda 1, these two term will become 0, and then you will get a c1. then replace s equals to minus lambda 2, you will get this first c1, this term, and this term, these two term will become 0, then you will get c2, and lastly if you replace s equals to minus lambda 3, you will get c3. So from here you will get c1, c2, c3, and then you put it over here, you just replace that value over here, c1 by here, let's say some kind of c1 plus lambda 1 is, and c2 by s plus lambda 2, and c3 by s plus lambda 3. You put the value of c1, c2, c3, then do the cross multiplication. What do you get? It's a c1 us by s plus lambda 1 plus c2 us by s plus lambda 2 plus c3 us by s plus lambda 3. Now you consider this term as a x1 s, this term as a x2s, and this term as a x3s. Either you can do this kind of thing, or you can choose x1, or you can choose x1s is equal to c1 us by s plus lambda 1, whichever you want to do this. So and x2 is similarly x2 is c2 us by s plus lambda 2, and x3s is equal to c3 us by s plus lambda 3. So now let's say I'm considering this thing, x1 is equal to this one. So if x1 s is equal to us by s plus lambda 1, now do the cross multiplication and then inverse Laplace transform. What you will get, x1 dot equals to minus lambda 1 x1 plus u. Similarly, you will get x2 dot equals to minus lambda 2 x2 plus u, and x3 dot equals to minus lambda 3 x3 plus u. Okay. And what y equals to get, this ys is equal to basically c1 x1s plus c2 x2s plus c3 x3s. Then inverse Laplace, we will get yt is equal to c1 x1 plus c2 x2 plus c3 x3. So therefore, the x1 dot x2 dot x3 dot is equal to minus lambda 1 minus lambda 2 minus lambda 3. So all the off diagonal, this means all the off diagonal elements are 0, x1, x2, sorry, x2, x3 plus 1, 1, 1. This is u, and y is equal to c1, c2, and c3. This is x1, x2, and x3. So since, as you see, the transfer function is a strictly strictly proper transfer function, so definitely we will never get the value at this d term. So d is basically over here is 0, right? So now let's do one example. So the example is, now consider an aircraft model. Okay. So the open loop transfer function, this OLTF means open loop transfer function, relating to normal acceleration ANS and input deflection command, which is delta CS, is approximated as, this is the term transfer function, minus 272 s square plus 1.9 s plus 84 divided by s plus 14, s minus 1.8, and s plus 4.9. So first of all, here already you are given basically here basically already you are given the roots of the denominator. So you did not do not need to find the roots of the denominator separately. So all the roots basically here, the lambda 1 is minus 14, lambda 2 is 1.8, and lambda 3 is minus 4.9. Okay. So what we have to do, we have to do this. We have to find out the plus 14 plus C2 is minus 1.8 and sorry plus C3 is plus 4.9. So we need to find out the C1, C2, C3 over here. So to find out the C1, C2, C3, the similar kind of thing you have to do. It's a 272 s square plus 1.9 s plus 84 is equal to C1 into s plus 4.9 into s minus 1.8 C2 into s plus 14 into s plus 4.9 and C3 into s plus 14 into s minus 1.8. Okay. So similarly, if you replace s equals to minus 14, yeah, s equals to minus 14, you will get C1, which is a value of C1 is 479.38, and then s equals to 1.8, you will get C2, whose value is minus 232.94, and s equals to minus 4.9, you will get C3 is equal to 440.32. Okay, so definitely ys by us is minus 479.38 divided by s plus 14 plus minus 232.94 divided by s plus sorry s minus 1.8 plus 440.32 divided by s plus 4.9. So if you do the cross multiplication and then taking this kind of thing, so let over here I'm taking x1 over is equal to minus 479.38 divided by s plus 14 into us. So what I will get, x1 dot equals to minus 14 x1 plus minus 479.38 ut. Similarly, x2 dot equals to 1.8 x1 minus 232.94 ut, and x3 dot equals to 4.9 x1 plus 440.32 ut. So what you will get, x1 dot x2 dot x3 dot is equals to minus 14 plus 1.8 minus 4.9 plus minus 479.38 minus 232.94 and 440.32 u, and y is equal to 111 x1 x2 x3, right? So is it clear to everyone? I mean, there is nothing to worry about. I mean, it is basically simple mathematics. Hello.
Yeah, yeah, yeah.
Yeah. So if instead of taking this constant term with definitely with x1s, then you will get this B matrix basically 1, 1, 1, and then C matrix is basically minus 479.38, minus 332.92, and 440.32. So this is basically the diagonal canonical form of strictly proper transfer function. So, first of all, let me ask you one thing. Do you have any kind of doubt from previous week and right now in this week? Does anyone?
I'm not confusing, but I think the definitions are somewhere we have to take the transpose and all those things, which is, I think, like in your.
Could you please start your doubt from the beginning? I just missed the beginning.
Yeah. See, suppose like in the controllable canonical form.
Yeah.
We only have to take means the values which we have to take is different from us observable one, right? Observable one, we have to do the transpose. Rest everything is the same.
In the observable, in the canonical form, this is basically your canonical form, right?
Correct. Controllable canonical. Yes.
Controllable canonical form. Yeah. And in the observable canonical form,
it's just the transpose one.
Yeah. So this is just a transpose. Exactly.
But here the U is means confusing, means how to calculate the U, maybe the input.
U is confusing means what confuses you basically?
Means can you please go down, because see there is a transposition of
no, C and B you have to interchange. C controllable transposes. It is sorry,
correct,
B controllable transposes, C observable.
Yeah. So means here from the controllable we have to transpose here the matrix, correct?
Yeah, in controllable, basically this is basically the relationship of controllable and observable form. So in controllable form, we basically take the in observable form, basically we need the output and input, because we know that all the output, all the state is not measurable, right? That's why we need the observer, and we need to design the observer, we need a observable canonical form. So for that case, we need to make a relationship between the output and input. So in that case, so I'm just not understanding what is your actual concern. I mean,
my actual concern is what is the reason behind having these different nature of canonical forms, means why sometimes we have observable and sometimes we have controllable. Is there something uniqueness, or means with the matrices we can conclude why is it that?
Okay, so as I told in the previous week, so when we the controllable canonical form, these two form, the controllable canonical form, observable canonical form, these two form basically known as a companion form. Okay, so so when we are talking about the system is controllable or not, or we need to design a controller, so that's why we then need this controllable canonical form. These forms is nothing but a simplification of basically we need to design something as a control engineer. We need to design either control input, or we need to design some kind of observer, or we need to analyze the controllability, observability, everything. We need to analyze this kind of thing, right? So these are all these transformations, all these forms, basically the canonical form. So in case of in diagonal or Jordan canonical form, basically using these canonical forms, we can analyze the controllability and observability, or we can analyze that state transition matrix very easily. Surely there is some kind of disadvantages of this transformation, because if you see the actual state in the actual matrix, if you see this, let's say if we talk about, so here Here in this HIV model, so the actual state are the T, T star, and V. But when we make it in a controllable canonical form, these x1, x2, x3 is not the actual state of the system, right? These are not the actual state of the system. So obviously, we cannot get the exact of anything using this transformation, because ultimately we have to apply our controller on this form. So this U, we have to apply this U, because we are basically design U. So we have to apply this U on this actual model. We cannot apply this U on the controllable canonical form and then we say, okay, system is controller. No, this is not possible. This controllable canonical form is advantageous for the controller to design the control input or design the control gain of the controller. Similarly, the observable canonical form is basically easier for the controller to design the observer. Okay, once we design the observer, we can say, okay, if this is the observer that we put in the system, and we can say that this observer basically estimate the actual state, not exactly. It is not possible that whatever the estimation and what is the actual state is completely exact, but there are some kind of error which can be ignorable. Like let's say there's some kind of epsilon error is there, but at least we can get the knowledge of the state, because there are few lot of state which we cannot measure directly because of the we cannot put the sensor exact that position, or we have some kind of financial issues, so that we cannot buy those kind of sensors which are very much costly. So for that case, we use the observer, and to design the observer, we need to this observer canonical form is basically easier to design the observer. So further in the in this course, when we comes to the this controller and observable term, controllability and observability, we will see the how this form basically comes into in picture basically. So these are not the exact replica
But
of the
Vivek,
system.
I got the point. Now it's clear, my doubt. But my one question still remains, like when we are using Simulink in MATLAB, it
Hmm.
gives separate results than what we generally do it in the practice.
Separate results.
Results, different results.
Different results in the sense, I mean, you do not
Suppose
get the,
A
yeah.
matrix and B matrix, so they are not the similar to what we generally see it in the what we are presently doing or what we are practicing.
So there's the first thing. If you, let's say here, just say, here I have chosen in this controllable canonical form, let's say, if you consider this, depends on how you basically choose these whole things. Okay, so here. So here we have considered that y is equal to x1, okay, as an output. And based on that, we have considered the x1 dot equals to x2, x2 dot equals to x3. Now, if instead of x1, if we say that y is equal to not x1, y is equal to, let's say, y is equal to, let's say, xn. So y dot, then it will become x1 instead of xn dot equals to this term, is you will get some kind of x1 dot equals to this term, this kind of term. It is based on your calculation, how you choose the output and how the all the values you will get. Because in if you follow the nice book, if you follow the nice book, you may not get the same exact value, exact matrix as the controller canonical form. This matrix you cannot get the exact. They mention this is basically the phase variable form, right? This is basically, if you follow the normal nice book, you can see that this is basically the phase variable form, and the controllable canonical form is something different. Uh, Let me just a minute. So so you can see in case of Norman Nice book, they have chosen y is equal to, let's say, y is equal to x3, then x3 dot equals to x2, then x2 dot equals to x1, then x1 dot equals to something minus a3, let's say minus a2 x2 minus a2 x3 a1 x 2 minus a naught, this kind of structure you use. So it's based on your calculation, which kind of, how you choose the state, how you choose the output. If already systems, yes, if you already if already system has given to you, all the question has given to you that okay, my output is x2 or my output is x3, then accordingly you have to find out the controlling, you have to find out the controllable canonical form. So let's say ki, in case of double integrated system, x double dot equals to a. So where a is basically the acceleration. Now x is basically the position. Now position, derivative of position is velocity, and derivative of velocity is acceleration, and acceleration basically my input. Now here, if you say that okay, by sensor I'm collecting the v, I'm measuring the v, not x. Okay, I'm measuring the velocity, not the position. Then you choose that y is equal to v, that is y is equal to, let's say, x2, and then x2 dot is equal to something. You have to do it accordingly. Okay, it's about okay, how you choose the states. It's not, I mean, the both approach is not the wrong approach. None of the approach is not the wrong approach.
So, means for exam point of view, we need to follow the approach what we are designing here, not the MATLAB approach, or how.
Yeah, you can follow, I mean, the in questions accordingly, according to your question. Let's say whenever you solve the multiple choice question, you have to check like how they have designed the parameters. Now let's say in case of let me just go to the one thing. So let's say in previous class also I get the same questions. So in case of, let's say, my GS is basically 2s square plus 3s plus 5 divided by s cube plus 6s square plus 11s plus 4. Okay, and you are asked to, and you are given basically this x dot is 0 0 minus 4 1 0 minus 11 0 1 minus 6 x plus a b c u, and y is equal to d e f x. So here in previous class, some of the one person, one student asked me like what I discussed with you, like I have chosen y is equal to x3 at that point, and then accordingly I have done the all this calculation, and I get this observable canonical form. Now instead of x3, if I choose x, y is equal to x1, do we actually get this kind of form or not? Do we actually get this kind of form? We never will, we will never get, because if we choose y is equal to x1, so how the observer will find is basically ys by us, just a minute, 2s square plus 3s plus 5 s cube plus 6s square plus 11s plus 4. So what we do is basically d3y by dt3 plus 6 d2y by dt2 plus 11 dy dt plus 4y is equals to 2 d2u by dt2 plus 3 du dt plus 5u. Now what we do, d3y by dt3 is equals to minus 6 d2y by dt2 plus, sorry, minus 11 dy dt minus 4y plus 2 d2u by dt2 plus 3 du dt plus 5u. If we do this kind of thing, 2u minus 6y plus d dt 3u minus 11y plus 5u minus 4y. Okay, so now if we do a triple time integration, so we will get this y is equal to 2u minus 6y dt plus this u minus 11y dt plus this 5u minus 4y dt. Now here I am choosing, let's say, sorry. Now let's say here I am choosing y is equal to x1. This whole term I'm considering as an x1. Instead of x3, I'm considering this whole term as a, let's say,
X1.
x1. So what way we will get y is equal to x1. So let's say this x2 dot x2 is basically, let me, so let's say this term is x3 and this term is x2. Okay, so x3 dot, what we will get, minus 4y plus 5u. So x3 dot is equal to minus 4x1 plus 5u, and x2 dot is equal to x3 plus, if you do not understand, please interrupt me and I will definitely explain you properly.
I got your point, but you are saying we are taking a different state, and from different state we are measuring, and it can have a different
Yes,
result.
different, because that x1, x2, and x3 in this observable canonical form or in this controllable canonical form, these are not the exact state of the system. These are the state that you are considering. That's why this is the disadvantage of this canonical form. Like, we cannot exactly represent the system using using this transformation form or using this canonical form. We cannot do that, but the property of the matrices are the same, so it is easier to design the controller and observer. But the thing is, how you choose the x3, how you choose the x1, it is based on you, because these are the state that you are choosing. These are not the state of the, these are not the internal state of any system. Okay.
But see, there are software like MathWorks software like uh, Simulink, what we say,
Hmm.
MATLAB.
Hmm.
So there the fundamentals should be like what they are taking the aspects. So means because
But actually, I have never used the MATLAB. I mean, never used MATLAB to find out the canonical form. So I don't know how they do that. I have to, let me check, and the next week definitely I will address you like how they do the controllable canonical structure and observable canonical structure, because I never use I mean, MATLAB to do this kind of thing. But
if you want, I
whatever
can
they,
share you. If you
huh?
want, I can share the screen. I have the
Yeah,
MATLAB ready. If you want, I can share.
yeah, okay. Share your screen.
Yeah, one moment. Is my screen shared?
Yeah, yeah, yeah. It's visible. It's visible.
See, basically, this is what we define any property like 4s square or 2s plus 5.
Sorry, actually, your MATLAB is not visible. Only your screen is visible. I mean that team screen is visible. You have to share the whole screen, not the particular
Yeah,
screen.
yeah. I have done that. Is it visible now?
Yeah, yeah, yes, it is visible.
So I have taken a system variable sys
Okay.
uh,
Ah,
some
yes.
variable where I have transformed
Yes,
this is
yes, I
my
understand. I
so
understand.
this is my canonical form and where I am getting these values,
Okay.
right? Whereas what we know is A matrix
Okay.
minus
So
2, minus 3,
first of all,
minus 5.
yeah, first of all, this modal decomposition is a different thing. Modal decomposition is not exactly you have studied yet. Okay, it's a different thing. I hope, I think in the later classes, we will definitely study this modal decomposition. This is basically a different thing, kind of approach.
So what decomposition we are using is generally okay. I maybe you are correct. That is what I wanted to know that.
Okay.
So are
So
we using any decomposition model or something?
no, this is that this is what I am basically trying to say is like, I don't know if MATLAB can do this controllable canonical form or observable canonical form kind of structure. I have no idea. So let me just give me just 1 week, because I have to check like what this canon function basically do, and what if what are the possibilities, like instead of this modal, what kind of others form they have. So I think this companion form is the this companion form is basically the, I think the controllable companion form is basically the uh, observable canonical form, and controllable companion form is basically sorry, the controllable companion form is basically the observable canonical form, and the observable companion form is basically the controllable canonical form. So I think that companion form is the
See, what is
basically,
one is DCF, that is diagonal canonical form.
I think
So that
this
is
is
a
diagonal canonical form. Yes,
this is diagonal canonical form, and the
yes.
other thing is OCF is observable
I
canonical form.
I think this is observable canonical form exactly.
For that, we use companion mode.
Hmm.
So
Yeah.
that is, I think, that is MATLAB has given in the properties. So that is
So
what I was trying.
I think that if when you use the companion form, you get the exact observable structure that you have studied in this course, right? I mean, there is nothing wrong with that.
Actually, I was trying to find the answers
Oh,
using this MATLAB, whatever the assignments we have got.
okay.
So,
So
but
you will not getting the exact
correct,
structure,
correct.
right?
Means my
So
answers were different, and so I was a
um,
bit confused.
okay. Right now, I can do only. I can say only one thing. Try to solve this using the hand equation, using this equation. I mean,
Yeah,
using your
I have
calculation.
done that
But
only. I have
yeah.
done that only.
So
I submitted.
let me. I mean, give me 1 week. So I will. I just check, because I never used this canon functions in MATLAB before. So I don't know exactly the what are the properties of these canon functions, and what are the
Got it.
model, what are the
No issues.
decomposition we can use. So maybe in the next class I can discuss this about. Okay,
Okay, sir.
it's
Okay.
not problem
Thank
to.
you, sir.
Yeah, right.
Thank you, sir.
So just stop sharing so that I can share my
I have stopped here.
yeah, I know that. So now move to the, let me just briefly discuss about how we can find the diagonal canonical form for the proper function, not the strictly proper function. And then we move to the Jordan canonical form, and then we'll discuss whatever the doubts you have. It won't take too much time, because So one thing I just need to ask you, like, and do you get the access of the previous week note, right? I mean,
Yeah,
did you?
I was able to download.
Sorry, you?
I was able to download this week's note also.
You are able to download, right?
Yes, yes.
Yeah, yeah. That's
No, notes in the sense, the notes which were there
I mean the
in the lecture
Google,
only, correct?
haha,
Google
the
Doc.
Google Drive link that I have shared with you. I mean, just this note. I mean, not note basically. This is basically the discussion. It's not note exactly. It's basically
Okay.
the. So did you get to download this note? I mean, is it possible for you to get this note, or
Yeah,
is
yeah,
there
I will.
any?
Yeah, I can download it now.
Okay, okay, that's it. So in the proper transfer function, so as we know, the proper transfer function means the degree of denominator and the degree of numerator both are similar. Okay, so since if since the degree of denominator and degree of numerator both are similar, so we cannot do the partial fraction method over here. So what we have to do, we have to make this proper function into a strictly proper function. How we can do that? So first of all, we know B3, we just multiplied it by mm, multiplied it with a denominator, and then we subtract the term which is extra, which is B3A2 S square plus B3A1 S plus B3A naught. These terms are extra, then plus B2 S square plus B1 S plus B naught whole divided by S cube plus A naught S square plus A1 S plus A naught. So in this manner, what we can get, we can separate the B3 term. B3 term means we can separate we are able to basically separate this term. And right now what we have basically B3, this is basically B2 minus B3A2 S square plus B1 minus B3A1 S plus V naught minus B3A naught whole divided by S cube plus A2 S square plus A1 S plus A naught. Now up to that point, you just make this proper transfer function into an improper transfer function with some kind of biasing term. This is the B3. And now you just do this same approach that we have applied in the previous case. This B3 plus now do this S plus lambda 1 plus C1 divided by S plus lambda 2 plus C3 divided by S plus lambda 3. Now find out the C1, C2, C3, comparing this equation, the comparing this term with the C1, C2, C3, and you will get the value of C1, C2, C3. And then in that case, after getting the value of C1, C2, C3, you have to multiply it US plus C1 US divided by S plus lambda 1 plus C2 US divided by S plus lambda 2 plus C3 US divided by S plus lambda 3. Now, if you consider this one as the x1, it's a B3 US plus C1 x1s plus C2 x2s plus C3 x3s. So you will get this kind of approach x1, x2, x3 to lambda 1, lambda 2, lambda 3. So basically here only in the output equation, you will get a d term. So in the output equation, you will get basically the D, so here D3 into U. Okay. So this is basically the diagonal canonical form for the proper transfer function. Now the Jordan canonical form, in Jordan canonical form, so let do a one small example for that, for this kind of form. So example is, let's say we have this GS, which is 3s square plus 2s plus 5 divided by s square plus 3s plus 2. Okay. So diagonal canonical form, what we have to do first, we know the, I mean, this is very easy. We know the root is s plus 1 into s plus 2, and this is 3s square plus 2s plus 5. So first of all, we have to do these things. 3 into s square plus 3s plus 2 minus, what I have to minus? 9s minus 6 plus 2s plus 5 divided by s plus 1 and s plus 2. What we will get? 3 plus here minus 7s minus 1 divided by s plus 1 s plus 2, right? So if you do this kind of thing, you will get, I mean, just normal partial fraction 3 plus c1 by s plus 1 plus c2 by s plus 2. What are the value of c1? C1 you will get minus 13. Sorry, c1 you will get 6 and c2 you will get minus 13. So what the value you will get? So gs is basically 3 plus 6 divided by s plus 1 plus minus 13 divided by s plus 2. Now it is easier for you to find out the state transfer function, because 3us plus 6us divided by s plus 1 and minus 13us divided by s plus 2. Okay. Now consider this x1s is equals to your, let's say I'm considering x1 is equal to 6us divided by s plus. So what I will get? X1 dot is equal to minus x1 is plus 6u. Similarly, x2 dot equals to, I will get minus 2x2 minus 13. What are the value? State space model diagonal canonical form will get minus 1 minus 2 x1 x2 6 minus 13 2, and y I will get 1 1 x1 x2 plus c into e. So this is basically the diagonal canonical form for the transfer function, which numerator and denominator have the same degree, that is proper transfer function. Now comes to the Jordan canonical form.
One confusion. What is the
Yeah.
difference between a diagonal canonical form and a control canonical form?
In controllable canonical form, there is nothing. I mean, you can see there is a no diagonal element, right? I mean, the diagonal element is not necessarily non-zero.
But it can be zero also, right? In a controllable canonical form.
I mean, in controllable canonical form, it is always that the last equation, the last row of the matrix, in controllable canonical form, the last row of the matrix is basically the coefficient of the characteristic equation, which is not the case for the diagonal canonical form, right? And in controllable canonical form, you can
So
see
means,
that the diagonal. Yes.
so diagonal is not controllable. It is only like it's not a controllable aspect. That is what I
No, it's not controllable aspect. Like when we need to design the controller for the basic purpose of controllable canonical form, as I said, that it is basically design the feedback controller thing. So that's why we need this design. Okay. But we cannot design the controller using the diagonal canonical form.
So what is the purpose of what is the advantage of having a diagonal or a Jordan canonical? Why do we need that?
So why do we need that? First of all, it is basically you will the later classes you can see the exact
Use of that.
exact use of the diagonal canonical form, because as I said, sometimes the matrix that we have, we need to we need a basically a similar transformations to do some kind of application, for some kind of application or for some kind of calculation. We need a similar transformation, and for the similarity transformation, first we need to check whether the system matrix that we have, does the matrix have a distinct eigenvalue or not. If the matrix have distinct eigenvalue, then you can directly say the system is a diagonal canonical form, and the system matrix and the similarity transformation is basically very easier. But it's not always possible, because there are so
So
many systems that there are similar eigenvalues. It's possible that all, let's say the system is three-dimensional and all the lambdas are same. So in that case, obviously we cannot guarantee, we cannot even for in case of similar similar eigenvalue case, we have to check all the eigenvectors are linearly independent or not. So do you know the term what is linearly independent? Do you have any idea what is linearly independent?
means
So when we say,
dependent on
let's say if we have a three vectors,
one is in X direction, Y direction, Z means
whatever. Let's say forget about x direction, y direction, z direction. I'm going to say that you have three vectors v1, v2, v3. So when you say these three vectors, when you can say these three vectors are linearly independent. When you can say this, that v1, v2, v3. I mean, obviously v1, v2, v3, you have the form of v1, v2, v3. I mean, I'm just.
because when the movement of one is not changing the other.
Could you explain it a little bit more? Not
Uh, Suppose
understand.
my motion is in such a way that the change of the direction of one of any one of the vector will not affect the any two others.
So basically, basically what you are trying to say is like the linear combination of these two. That means we cannot represent v1 in terms of any v1, v2 plus v3. It is not possible. Let's say v2 is not possible in terms of v1 and v3, or v3 is not possible to, or let's say this is not the exact actually. So basically, the exact thing is, let's say I have alpha 1 v1. If I multiply this vector with some kind of scalar alpha 2 v2 and alpha 3 v3, and I get the value of 0. If this alpha 1, alpha 2 and alpha 3, these are not equals to 0, or any of these are not equals to 0. Let's say I have the vector v1 is equal to 1 0 0, v2 is equal to 0 1 0, and v3 is equal to 2 3 0. So this V1, V2, V3, are these V1, V2, V3 are linearly independent or not? So what we can say, we know that V3 can be represented as 2 into V1 plus 3 into V2, right? Right? So that means if we do this kind of thing, like 2 into V1 plus 3 into V2 minus V3, we will get a 0, 0, 0 vector, right? So that means since V3 is depend on V1 and V2, V3 is not independent of V1 and V2. So we cannot say this V1, V2, V3 are linearly independent. But if we have V1 is equal to, let's say, 1, 0, 0, V2 is equal to 0, 1, 0, and V3 is equal to 1 or 2.
0, 0, 1.
So it's 2, 2, 3, 1. 2, 3, 1. Now we cannot represent V3 in terms of V1 plus V2 because there is a one term over. Because of this term, these three vectors are linearly independent. That means the alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equals to 0 only possible when alpha 1 equals to alpha 2 equals to alpha 3 is equals to 0. At that position only this combination will become 0. Otherwise, this combination will never become 0 for this case. So here V1, V2, V3 are linearly independent. So in the latter courses, obviously you can see that we need to find out the linearly independent eigenvalue. So when we have a distinct linearly independent eigenvector, sorry. So when we have a distinct eigenvalue, so obviously we can guarantee that our eigenvectors are linearly independent because for lambda 1 we get defined eigenvalues with eigenvector, for lambda 2 we get defined eigenvector, for lambda 3 we get defined eigenvector. So these eigenvectors are different. So we can say that system is diagonalizable. So we can do the similarity transfer. But
So
sometimes, yeah,
on,
yes.
on a broader sense, Jordan canonical form is not used for controllability.
Jordan canonical form is
Not used for controllability of
that it can also use to check the controllability and observability, and also it is used to basically find out the state transition matrix. And also there are also looser form of controllability and observability which are called detectability and stabilizability. So yeah, we can do that using the Jordan canonical form.
no, just now just now you said that since they are diagonal and since there are no values in the later end, so they cannot be represented as a controllable matrix.
That we can check that whether it is possible if the system have a different eigenvalues. If the system has a similar eigenvalues, can we can we transform it into a controllable canonical form or not? That is a different kind of thing. But this doesn't mean that Jordan canonical form, if the system have a similar eigenvalue, doesn't mean that system is not represented into a controllable canonical form. No, we have to check whether it is possible or not. But yes, the system may be diagonalizable, may not be diagonalizable. This is the different thing. Diagonalizable means all the eigenvalues in the diagonal form, but sometimes it is not possible that all the eigenvalues are distinct. When we get the similar eigenvalue, we will not get the exact diagonal form. So when we have the exact diagonal form, it is, I mean, ये मतलब बहुत बाद का chapters है. I cannot if I discuss it right now, you have to
Okay,
know the all the things.
I got the point. Means you are saying that means what an idea I am getting is the basics. What is there is yes, most of the time or maximum uh, probability is that the Jordan canonical form
Yeah,
is used for controllability and observability. But
yeah,
there are exceptions
yeah.
where it cannot be used for controllability and observability.
I mean, you have. I mean, obviously
probability of this is very less, or maybe neglected. Or
yeah, I mean, most of the cases, like checking of controllability and observability doesn't mean the system is a controllable or observable. I mean, if checking means whether the system is a controllable or not, this checking, I mean, this type of this diagonal form or Jordan form, these two forms are basically primarily used to check the controllability, stabilizability, detectability. It's like whether the system is stabilizable or not, whether the system is detectable or not, whether the system is observable or not, whether the system is controllable or not. I mean, yes or no, both is basically a checking, right? When I say that I'm checking the controllability of a system, I'm checking that whether if I is there any control input, there exists any control input which transfer the system state from x0 to x1 with a finite time. Is it possible? This is basically a controllability. Like मैं यहाँ से कोई एक पॉइंट से दूसरे पॉइंट पर स्टेट को जाने के लिए मेरे पास ऐसा कोई कंट्रोल इनपुट है कि नहीं, तो ये चेक करने के लिए कि है कि नहीं, वी यूज दिस काइंड ऑफ फॉर्म। अब है कि नहीं वो देखने के लिए कि ओके है, तो उसके लिए उसका कंडीशन क्या है, दैट डजंट डिफाइन द डायगोनल फॉर्म और जॉर्डन फॉर्म। उसके लिए अलग डेफिनेशन, अलग डिफाइनिंग क्राइटेरिया है, क्योंकि अगर ये सेटिस्फाई होता है देन सिस्टम इज कंट्रोलेबल, इफ दिस डज नॉट सेटिस्फाई देन सिस्टम इज नॉट कंट्रोलेबल। दिस इज अ डिफरेंट थिंग। तो चेकिंग इज, हाँ, चेकिंग इज डिफरेंट थिंग एंड इट इज पॉसिबल और नॉट, उसके लिए जो क्राइटेरिया है दैट इज अ डिफरेंट थिंग व्हिच यू विल स्टडी इन द लेटर वीक्स बेसिकली। So this is not the topic of this week. I'm sorry.
no, actually,
Sorry. Yeah.
actually, I am only confused with one word: the controllable canonical form, and the means I thought controllable canonical form is only for controlling, observable form is only for observing, and these.
You are I mean quite right. It is basically controllable canonical form is basically used. It is easy to design a controller if we can represent the system metric in a controllable canonical form. तो अगर मैं किसी सिस्टम मैट्रिक्स को कंट्रोलर कैनोनिकल फॉर्म में ट्रांसफर कर पाता हूँ, देन मेरे लिए उस सिस्टम का कंट्रोलर डिजाइन करना, लेट्स से स्टेट फीडबैक कंट्रोल, मैं u इज इक्वल टू माइनस के एक्स देना चाहता हूँ सिस्टम में। मेरा सिस्टम का जो इनपुट होगा u इज इक्वल टू माइनस के एक्स, मैं स्टेट फीडबैक देना चाहता हूँ। तो स्टेट फीडबैक देने के लिए मुझे k को डिफाइन करना पड़ेगा, राइट? बिकॉज वी डू नॉट नो द व्हाट इज द गेन आई हैव टू गिव ओवर हियर, आई हैव टू चूज। तो ये जो गेन हम लोग चूज कर रहे हैं, ये गेन को चूज करने के लिए अगर मैं सिस्टम मैट्रिक्स को एक कंट्रोलेबल कैनोनिकल फॉर्म में ट्रांसफर कर पाऊं, देन इट इज इजियर फॉर अस टू डिजाइन द कंट्रोलर, दैट इज टू डिजाइन द के। एंड ऑब्जर्वेबल कैनोनिकल फॉर्म इज व्हेन वी नीड और ऑब्जर्वर। तो ऑब्जर्वर को डिजाइन करने के लिए अगर मैं सिस्टम मैट्रिक्स को एक ऑब्जर्वेबल कैनोनिकल फॉर्म में लेके जाता हूँ, तो इट इज इजियर फॉर अस टू डिजाइन the observer.
But this Jordan and diagonal is
This
only
is
for the
this,
repeat.
these
Only for the repeated role, and maybe for controllable or observer. It can be for controllable or it can be for observable.
controllable, canonical, observable, but these type of these two forms, this diagonal canonical form or Jordan canonical form, these two forms generally not used to design the controller or to design the observer. These are basically normally used to analyze the state transition matrix. So I hope you know the state transition matrix. Do you have any idea what is the state transition matrix? Yeah.
State transition matrix.
To determine the state transition matrix or to analyze the system controllability, तो ये सब करने के लिए बेसिकली हम लोग ये तुम्हारा जॉर्डन कैनोनिकल फॉर्म एंड डायगोनल कैनोनिकल फॉर्म यूज करते हैं। बट ये कंट्रोलर डिजाइन या ऑब्जर्वर डिजाइन के लिए नॉर्मली ये यूज नहीं होता है, ये बेसिकली यूज नहीं होता है। जो हम लोग नॉर्मली यूज करते हैं दैट वाज द कंपेनियन फॉर्म व्हिच वी हैव डिस्कस्ड इन द प्रीवियस क्लास, प्रीवियस वीक। ओके,
it may be or it may not be used for maybe for controllable.
So just let me discuss a little bit about Jordan canonical form and then So here I'm just using the proper transfer function plus b1 is plus b naught divided by s3 plus a naught b2 is square plus a1 is plus input. And now let's say this system has b3 is cubed with s1 is just b naught, and this is, let's say, s p1 whole square into s plus p3. Okay. So what we do, first of all, since the numerator and denominator have same degree, we have to separate this b3 term. Just similarly, the previous case, जो हम लोगों ने proper transformation for diagonal canonical form के लिए हम लोग किया, we separate the b3 term and we will have some numerator, let's say b2 minus b3 a2 square plus b1 minus b3 a1 s plus b naught minus b3 into a naught divided by sp1 square plus sp3. So now what we do, b3 is equal to, let's say, some d1 s plus p1 square plus d2 s plus p1 plus d3 s plus p3. Similarly, जैसे हम लोग the way we did the uh, mm, partial fraction, so similar approach. Now we have to find out the value of d3, sorry, d1, d2, and d3. Once we have find out the values and then we cross multiplied it, so ys is equal to, now this is a similar thing, d1 into us divided by s plus p1 square plus d2 us s plus p1 and d3 us s plus p3. Okay. So here the one problem is, let's say I am choosing x1 s is equal to us by s plus p1 square, x2 s is equal to us divided by s plus p1, and x3s is equal to us divided by s plus p3. So since it is quite difficult to find that inverse Laplace transform of this kind of structure, so what we do the x1s divided by x2s. What we will get, us divided by s plus p1 whole square into s plus p1 divided by us. We will get this. So what we get now, cross multiply and then inverse Laplace transformation, we will get this formation. So what we get, x1 dot equals to minus p1 x1 plus x2. Similarly, x2 dot, it is not difficult for this case, so obviously x2 dot equals to minus p1 x2 plus u, and x3 dot equals to minus p3 x3 plus u. So what you will get, and y is equal to b3u plus d1 x1 plus d2 x2 plus d3 x3. So what you get, x1 dot x2 dot x3 dot, it's a minus p1 minus p1 minus p3. So instead of 0 here, 1 0 0 0 0, x1 x2 x3 plus 0 1 1 u y is equal to d1, d2, d3, x1, x2, x3, and here d3 into e. So you can see that one thing in case of Jordan canonical form, basically here this term is 1 and this term is 0. But in case of diagonal canonical form, this term is 0 and this term is 1. So this is basically the difference that you can see. Now, if your, let's say, so if let's say your system is instead of, let the system as eigenvalues all eigenvalues are same. So in that case, you will get x1, x2, x3 dot. But definitely you will get, let's say, minus p1, minus p1, minus p1, and this is 1. You will get only this term, this kind of structure. Okay. So here, this is the one, this one is one Jordan block, and this one is another Jordan block. This Jordan block corresponding to lambda 1, sorry, corresponding to P1, and this Jordan block corresponding to P3. So here there is only one Jordan block. There is no two Jordan block. Only one Jordan block you will get because all the eigenvalues are same. So you will get one Jordan block. So here is basically Jordan block corresponding P1. So basically you will get the structure some kind of J1, J2, J3 and dot dot dot. Like basically you will get the structure some kind of system matrix J1, J2, J3, and let's say there are m eigenvalues, so Jn. So each Jordan block corresponds to each similar eigenvalue. So this Jordan block corresponds to lambda 1, let's say this corresponds to lambda 2, this corresponds to lambda 3, this corresponds to lambda n. Okay. So this kind of structure you will get. So this is basically the Jordan canonical form. So, so, uh, so is there any kind of doubt right now? Or I mean, only one person is basically attending this class. So I hope all the doubts that you have, I am able to clear it. If not, then right now, yeah. Sorry, your voice is breaking. Can you please speak loudly?
Yeah, it was very nice because some of the doubts you have cleared my end
Okay.
because I was struggling
Okay.
for last week.
Okay.
Thank you so much.
Thank you very much. And okay, let's meet next week. So since there is no doubt, I'm just stop this recording, and I will definitely upload this video and also the this note in YouTube and Drive. You can access it. Okay. Thank you. Yeah.
Thank you, sir.